What?
All right. I want to talk about. We're going to wrap up talking about rational functions in which the numerator is, or the leading degree of the numerator is smaller than the leading degree of the denominator. Tomorrow we'll work strictly on the idea of when the numerator is bigger than the denominator, and also you guys can ask some questions more about homework, stuff like that. But it says in this line, we worked on this one yesterday, but I want to finish up because the bell rang, and I just want to make sure that we have this concept understood because it becomes very important, and it's one of the things that throws people off because it doesn't always happen. Think about taking two functions. One in your, or two polynomials, one in the numerator, one in the denominator, and you factor them. Not always will there be common factors. Okay, I don't want to say it's rare, but it doesn't always happen. And you might go through 5, 6, 7 problems in homework where it doesn't happen, and you might just kind of train yourself to not even worry about common factors. And then when you get a problem that has common factors, you've trained yourself not to look at them. Does that make sense? I want to make sure that we're training ourselves, even though they might not exist every single time, to pay attention and try to figure them out. Okay, see if they're already there and see how that applies to the work. It says so check for common factors. If you have common factors, what it does is it provides holes, or what we call point discontinuity. That's kind of the math word at the zero provided by that factor. Okay. Now when I say at the zero provided by that factor, it simply means I take that factor, set it equal to 0, and solve. Okay. And that will give me the x-coordinate of where the hole is. Okay. Now when I say 0 in that situation there, it is not the same thing as an x-intercept or a root. Okay. It's going to be, sometimes the hole will be on those, will be an x-intercept, or where an x-intercept would show up. But when I say this 0 here, I'm just meaning that I took the factor that these two things had in common and I set it equal to 0. Okay. And solve for that. So that will give you the x value of the hole. Okay. We then want to plug that x value into the reduced r of x. Okay, the reduced rational function, to find the appropriate y value for the hole. Okay, and when you graph it, you're going to graph it with an open dot. All right. What is important for us to understand, and I know a lot of us like to use our technology, and I hope we use our technology to not do the word for us, but to verify the word. Your technology doesn't have the ability to graph open dots. Okay, you could graph this thing on your calculator. And you're going to get something that looks on your calculator kind of like that. Okay, so let's say we're on, a chapter test, you're on WebAssign, you're on an ACT or something like that, and you've got options. Let's say this is option A, and this is option B. Let's say option B looks like this, looks the same, but there's a hole right there. Okay. If you type it into your calculator and you're just using the calculator to allow you to make judgments, your calculator is going to show you the green one. But in all reality, the red one is the one you want to choose. Does that make sense? Okay. Your calculator, and even GeoGebra, or we opened up Desmos last period, they don't have the ability to put those holes in there. Okay. I have seen some online platforms that have calculators in them that will generate a graph that has a hole in it, but obviously on ACT or chapter test, something like that, you're not using those things. So once we do that, once we find those common factors, we're then left with a reduced function. We're going to do everything that we've done: vertical asymptotes, horizontal asymptotes, crossing horizontal asymptotes, x-intercepts and y-intercepts, using the reduced version. Okay, just makes things a lot easier algebraically, and we get the same results if we would have used the original function. Okay, so first thing we want to do is factor this thing. So we're at s of x. This one's kind of easy in regards to the factoring part, x, and then x minus 3 on the bottom, right? Okay. So the thing that we recognize is that that thing and that thing are common factors, right? And as you go through multiple examples, you could have as many common factors as they want. Okay, you could have 3, 4, 5 common factors. And that would mean you'd have 3, 4, 5 holes, right? You're gonna have a finite set of holes, but you however many factors that repeat up top and the bottom, you're going to have holes there. Okay, so what we do is we take that x minus 3, okay, doing this idea right here. If x minus 3 is set equal to 0, then x equals 3. Okay, so I've just found the 0 of that factor, x minus 3, and that tells me the location of the hole on the x-axis. Okay, now it doesn't mean that the point is going to be on the x-axis, it just tells me the x location of my hole, right? I want to know what the y location is. Okay, so basically what we're going to do is we're going to treat this thing as a point that does exist, and the way I find y values of points that do exist is I take that x value and I plug it back into my function, right? Plug that back into my function, evaluate, and it should give me a y value back, correct? Okay, so let's do that. Let's think about this. If I plug in 3 to this original function, or to the factored one, what do you get up top? 0. What do you get on the bottom? 0. Can you do that? 0 over 0? No. Okay. Even though it's the same thing divided by itself. Okay. Like 1 over 1 is 1. 2 over 2 is 1. 3 over 3 is 1. Right? 0 over 0 is not 1 because 0 over 0, the division of 0 takes precedence, supersedes any other rule. Right? Okay. So it's still an undetermined quantity. So you don't plug back into there. And the reason I kind of forced you to do it is to hopefully see if you accidentally make a mistake and you do plug it back into that one, you realize that the math tells you, nope, that was the wrong one to plug into. Does that make sense? Okay, because you should get a quantity back. You should get a known value back that you can actually deal with. So what happens is we don't want to plug back into the original one. We want to plug back in to the reduced one. Okay, so the reduced one is s of x is 1 over x, right? Plug x back into that one, what do you get? 1/3. Okay? So right now that tells me when x is 3, y is 1/3, and that's a hole. Okay? Now, like I said, if you graph this on your TI-83 or 84, you typed in x minus 3 over x squared minus 3x, it's not going to show an open dot there. It's going to show a closed dot like nothing's wrong. Okay? And even the technology that we have is not going to provide you with that 1/3. Okay, we go to we plot this thing here, graph that in y1, go to our table, it's going to say 3, error, okay, because there's no point there. Okay, so it doesn't have the ability to plug 3 in and get a y value back because it's trying to plug 3 into this thing. Okay, I'll show you a technique. You gotta be thoughtful, but I'll show you a technique that will give you this 1/3. But we'll get there towards the end of the problem. Okay? So now everything that we do in regards to kind of what we've talked about yesterday and the day before is that we're going to find vertical asymptotes, we're going to find horizontal asymptotes, we're going to find your intercepts, so x and y intercepts. Okay, and actually I'm going to write those as individual. Intercept, y-intercept, and then if we need to, we can find some test points. Okay, but we're going to do all this stuff with the function s of x equals 1 over x. Okay, with the reduced version. Because now if I look at this, I find a vertical asymptote. My vertical asymptote is when the denominator cannot be 0, right? So when is that going to happen? X when x is what? 0. X is 0. So it's a vertical asymptote. This is why we want to look at the reduced version. If I look at this version, it tells me I have a vertical asymptote at 0 and I have a vertical asymptote at 3, right? Okay. Well, I have a hole at 3. Holes take precedence over asymptotes. You can't have a asymptote. You can't have an asymptote and a hole at the same place. Does that make sense? Okay. So you always want to look at the reduced version when you're finding your asymptotes. The next thing is I want to find my horizontal asymptote. Okay, so finding my horizontal asymptote, we're going to look at the leading degrees. Okay, now you probably would never write this, but what I want you to understand is that this 1 is actually x to the 0, right? And this x to the first there. If I compare those, 0 is less than 1, right? So then when the numerator is smaller than the denominator, you will always have a horizontal asymptote at y equals 0. And if that confuses you, if you're not sure, plug in some arbitrary values for x that are really big into your reduced version. If I plug in x to be 10, I get 1 over 10. If I plug it x to be 100, I get 1 over 100, okay, or 0.001, okay? Or I get 1,000, 0.0001, okay? And I keep getting smaller and smaller and smaller numbers, right? Okay? So hopefully that shows you that in the long run, as x gets really, really big, you approach that number, okay? And that's the one thing you can do with horizontal asymptotes. If you're not confident in your remembering of the 3 rules, or 3 concepts, or 3 hopefully you learn the math and that explains those 3 properties. But you can plug values in, kind of in a repetitive process. Plug in, x is 100, x is 1,000, x is 10,000, and then see what is happening to those y values, and you can kind of make a good judgment then about what your horizontal asymptote is. Okay. Now, here's where I think maybe our mathematics has gotten us kind of ingrained in a mode in our lives that we just want to do the work, we want to do the process, the steps, get an answer, and move on, right? And do the exact same thing every single time, okay? But what I want you guys to start trying to force yourself to do is when you get information, when you get a result, think about what that result is telling you, okay? When I get a vertical asymptote at x equals 0, okay, there's a lot of information hidden behind that. And what I mean by that is x equals 0 is what axis? It's the y-axis, right? Okay. And if x equals 0 is my y-axis, and I want to find y-intercepts eventually, if I got a vertical asymptote through the y-axis, can I have a y-intercept? No. Okay. So this right here, once I found that, it also told me that y-intercepts are not applicable. I don't have any. Okay. They don't exist. Does that make sense? Okay. So don't just blindly start doing the work and kind of be robotic about things. Go through and when you find a value, you find a result, think about what that means to you. Okay? Now, we can't do the same thing with the horizontal asymptote and x-intercept. Even though we get y equals 0, and that's a horizontal asymptote, we have talked in the past that you can cross horizontal asymptotes, right? So you might have that situation. So saying that my horizontal asymptote y equals 0 does not say that these are not applicable. Okay? However, we can get to that point pretty quickly. Remember, if we want to cross horizontal asymptotes, or if we want to check to see if we cross horizontal asymptotes, we take our original function, 1 over x, okay? And we take our horizontal asymptote, y equals 0. And basically what we have is 2 equations. We have y equals 1 over x and y equals 0, okay? Now that's a system of equations because they both have 2 variables, right? And the same 2 variables. But they're nonlinear, okay? Which is maybe something we haven't worked with a whole lot in the past. But to solve nonlinear systems, the best approach is to use substitution. Okay? Right now we know that these 2 y's are the same, right? Okay, so can I take that y right there and replace it with that 0? So I get the new equation, 0 equals 1 over x. Okay? Whatever the function is, whatever the equation is, when it's a denominator, when there is a fraction, don't you want to multiply everything by the least common denominator? So what's the least common denominator here? X, right? Okay? Or 1x if you want to do that. I'll multiply by x over here, multiply x over here. Okay? What do I get when I multiply x over here? 1. And what do I get over here? 0. So I now get a statement that says 0 is equal to 1. If you remember yesterday, we got an equation that was like 5x equals 0. And that provided us a true statement when x was 0, right? Is there any x value that you can plug into 0 equals 1 that would ever give you a true statement? No, there's no place to plug in, right? That is a false. 0 never equals 1. This is a false statement. So when you get false statements, okay, back to Algebra 1, when you get false statements, it tells you that those things do not cross. Does that make sense? And you've seen this, you see it here on the whiteboard. I had it from the last class, but we'll use something maybe a little bit different. If I've got y equals I don't know, like negative 3x plus 12 and y equals negative 3x plus 15. Okay, think about this. Those two equations have the same slope, right? So what's that tell you about those graphs, those lines? They're parallel. They don't cross, right? Well, the algebra that would tell you that is if you take negative 3x plus 12 is equal to negative 3x plus 15. The negative 3x's cancel each other out, right? So you get 12 equals 15. Okay? And some people might even go as far as saying, well, subtract 12 from both sides and get 0 is equal to 3. Well, either one of those is a false statement, right? Okay? And that false statement that we get from that algebra verifies or confirms the idea that these things were parallel, that they don't cross. And it's the same thing there. Okay? The same logic with nonlinear systems that we learned with linear systems. Okay? So we don't cross the horizontal asymptote. So the horizontal asymptote was the x-axis, right? So if you don't cross the x-axis, you don't have any x-intercepts. Okay? So understanding that logic hopefully alleviates you from doing some work for x-intercepts and y-intercepts. Even though if you went through and did the work for x-intercepts and y-intercepts, you're going to find out that that's not really hard. Well, some people might say, well, when I want to find an x-intercept, that means y is 0, so I plug 0 in and I get 0 equals 1 again, and not really know what that means. With using this idea and this logic, we know we don't even have to check that. We don't even have to deal with x and y intercepts. Saves you a little bit of time, and that's kind of the hope that as you start learning mathematics kind of at a deeper level, it's about understanding. It's not about how many problems you can calculate and how fast you can do the arithmetic and that kind of stuff. It's about, do you understand what you're doing and what it's telling you. So now when we graph this, okay, we had a horizontal asymptote there. We had a vertical asymptote there. Now, because we didn't have any x-intercepts or y-intercepts, we really don't have a whole lot of information here for our graph in regards to like test points. But we do have the idea that we had a hole at, what was it, 3 1/3? Okay. So if I have a hole at 3 1/3, 1, 2, 3, and 1/3, maybe about right there. Okay. What it means, what hole or a hole or point discontinuity is that I can graph the whole thing. We were talking about continuity being the idea of we take the curve and we can trace it without ever lifting our pencil, right? Okay. Well, point discontinuity or holes is that idea. I can trace the whole thing except for at one point. I gotta lift my pencil, jump across that point, and then I can finish, right? So there's only one issue. So if that's the only one issue, okay, so I skip that point, and I go to the next point right after it in both directions. That means that the curve has to exist in that same region that the hole was in. Does that make sense? It can't be on the other side of the asymptote. All right. So that's kind of what my graph is going to look like there. If you weren't confident in that, by all means, you've got the option, you've got the ability to, and my graph is kind of terrible in regards to scale, because if s of x is 1 over x, I should have the point 1 comma 1, right? I should have the point 2 comma half. I should have the point half comma 2. So it's actually kind of more like that, okay? But if you're not sure, once you've got all your x-intercepts, your y-intercepts, your holes, and that kind of stuff, and you're not sure where your graph should exist, by all means, take x values and plug them in and get y values back and plot those additional points. So for instance, I don't know where the graph's going to exist over here. Okay? So I'm going to take s of x equals 1 over x, and I'll plug in, x to equal -1, because that's over here, right? It's an x value in these regions. Well, if I plug x equals -1, what do I get right there? -1. Okay? So x being -1, y is -1. I get that point right there, right? So now I get that point in that region. All the other points are in the same region, right? Okay, because we know we can't cross over this asymptote, so we're not going to kind of filter over into this region. And we also know that we've done the math to show that we never cross this horizontal asymptote, so I can't filter over into this region. So this curve has to do something like that. Okay? Where that, if you were to graph that on your calculator, okay, or the calculators that we've been using in class for a good portion of the class, whether it be GeoGebra, Desmos, TI-83 or 4. I showed you last week Wolfram Alpha. Whenever you type something into Wolfram Alpha, it's going to give you the graph every time. So you plot every time that function. It does not always put these holes in. Okay, I have seen things on Wolfram Alpha every once in a while where it does put a hole in. I typed this one in earlier and it didn't give me a hole. Okay, so I don't know the reasoning for that, but if you type it in the calculus, if I go to y equals, I got that typed into y1. Typed into y1, and I'm going to just make sure my window is set up to see an x value of 3. So I want to show you what the graph is going to do where your hole exists. So if I graph this, I get something like that, right? And my hole should actually exist where my cursor is. Okay, but you see that it looks continuous there, right? So if you're using your calculator, if you're on WebAssign, and just type in your calculator, your function in your calculator and determine what the graph looks like so you can choose the option, that's fine. But understand that your calculator is not representing potential holes that may exist. So that might be something you want to do at the onset first, okay? Or if you're using your calculator to do that, that's okay. But before you look at the graph, come to your table and look at your table, okay? Now this won't always work because of how our table is set up. Our table is not showing us the infinite x values, right? Right now my table is just set up to show me my integers. Okay, so if I had a hole at like 0.5, my calculator is not showing that, right? Okay, so I have to maybe change my table change. Okay, if we go to second table set here, go to my changing table, maybe take it to 0.5. And now you would see that, if I had a hole at a half or 3/2 or something like that, now it would show it over there. Does that make sense? Okay. But again, without doing the algebra, without doing stuff by hand, you don't know how to set that table up. Okay, you don't know how to develop that changing table. But as I go through here, you start to see errors on the right-hand side. Understand what these errors mean. Okay, you're going to get an error when you have x equaling 0. Well, think about my graph. When x was equal to 0, what was there? What was showing up in your graph when x is equal to 0? Yeah, vertical asymptote, right? Okay, so that's what that error means. Okay, so if I keep going down then to x to be 3, I get another error. Okay, understand they don't differentiate in what type of error it is. It just means that there's not a point that exists there. It means that when it plugged 3 into y1, it got an indeterminate value. You got division by 0. Okay, so they don't differentiate whether it's an error because of asymptotes or an error because of a hole. This is an error because of your hole. Does that make sense? Okay. Now here's how you could find, because we did the work by hand up here to find that 1/3, right? We simply plugged plug 3 back into the reduced function, correct? Well, if you want to use your calculator to help you do this, that's fine. You just have to type the reduced function into y2. So 1/x is that reduced function, okay? And then you're going to go back to your table. And I'm going to go down to where I saw the hole. The hole was at 3, so that's the x value of 3. And then when you plug that 3 into the reduced function to find the y value is that 1/3. Does that kind of make sense? Okay. Not saying that that's the, obviously if that number comes out to be a pretty nasty number, 0.33333, we can infer that's a third. But if it's like 0.2187 or something like that, do we know what that is? Okay? So that's an option. That's a tool that you can use to work through some of these things. I want to do another one. Let's take R of x. Let's let that equal, let's go x squared plus 3x minus 10. On the bottom, let's go x plus 1, x minus 3, x plus 5. Okay, so we're looking at that function. Now let's think about this. The numerator is quadratic, right? The denominator is what? Cubic. Okay. Now here's the thing, and you just got to be, kind of think about how I have to write a test, or how the roads instructors have to write tests and stuff like that. If we've got an hour and a half to do a test, and we've got, these are pretty long processes, right? I probably can't give you 5 or 6 of these questions. I give you maybe 1 or 2. And the first step of all of these is the factor, right? I can't give you something up here that's like 4th degree and something down here that's like 5th or 6th degree and ask you, and write them in expanded form and ask you to factor them in that hour and 25 minutes to take that test. Because there's other things that we have to test over, right? And that might take you, 25 minutes to do that one problem, okay? So, in the event that I give you one of these on the test, okay, and you have to use all your factoring techniques. We wrote those on the board over here. We had factor by GCF, we have the product times sum technique, we have the AC method, we have the quadratic formula, and then if none of those work, we have the rational root theorem, right? If none of those work, you have to use the rational root theorem for these, okay? I'm going to write it so that you only have to do the rational root theorem for just maybe the numerator or just the denominator. Does that make sense? If I were to look at this one here and factor that out, or FOIL that out, it'd be like x to the third plus x squared, so some x squared plus some x minus 15. And you would have to use P over Q to factor that to get this down to this. Does that make sense? So I would have to provide you, maybe alleviate some of the work for you, or maybe say, okay, this bottom one, an expanded version looks like this, but one of the zeros is -1. Can you do the work to find the rest of them and factor the rest of that thing? Does that make sense? So understand that, if you're worried about how you may have to factor, yes, I'm going to kind of force you to use all your factoring tools, but in a manner that shows me that you know what you're doing and you know the concept, but in a manner that doesn't make you spend a half hour per problem. Okay. So in this one, they already do some of the work for you. They alleviated some of the work and they did the bottom for you. We factor the top. What's the top factor to it? All right, x plus 5, x minus 2. All right, maybe this one. There you go. X plus 5, x minus 2. And then on the bottom we have x plus 1, x minus 3, x plus 5, right? First thing you always want to do is what? Great, yeah, check for common factors. So if I got x plus 5 here, and I got an x plus 5 there, right? Okay, so those things are going to reduce. And then if we look at that, think about, just any other fractions you ever looked at, or any other ratios you ever looked at. If I have like 12 over 4, okay? Isn't that the same thing as 3 times 4 over 4? And we cancel those because that's a factor of what? What's 4 over 4? It's just 1. So what's x plus 5 over x plus 5? It's just 1. Okay? So they do cancel, but algebraically we know, even though they cancel, if I chose -5 and plugged it through this thing right here, okay, even though they cancel, I'd have a 0 up here times this stuff, a 0 down here times this stuff. It gives me 0 over 0, and you can't do that, right? So you do have to realize that it is kind of impacting the mathematics, even though they do cancel. So I want to say x plus 5 equals to 0. That's going to be x to equal -5, right? And that's where we have a hole. Okay. Now my reduced version of this thing, after we cancel things out, right over here in red, we have x minus 2 over x plus 1, x minus 3. Once you find that you have a hole at x equals -5, you're going to take that -5 and plug it into the reduced version to find the appropriate y value. Okay, so when I plug that -5 in up here, you're going to get y equals, in the numerator, you get -7, right? And on the bottom, you're going to get 32? Positive 32? Negative? Sure?
No, it's positive.
It's going to be a -4, right? It's going to be a -8. It's going to be positive. All right, so that's, -7 over 28 would be -1/4, right? So that's going to be a little bit less, maybe like -0.2 or something like that. And now the hole. So that's the x value, that's the y value. So you have a hole at -5, -7, 30 seconds. Okay. The thing with like WebAssign or how they want you to answer it in some test or the ACT or whatever, your option might not be the decimal of that. You might, so using your calculator and typing in, this in the y1 and this in the y2 like we did in the last example, and seeing, I have an error at -5, and then the y value of that error would give me some decimal. Maybe that decimal is not one of your options. Does that make sense? And you would have to know what the fraction is. Okay, so this is the way that we would know that fraction. Next thing we do is we go and we try to find our vertical asymptotes. Okay. Now everything that we do then at this point, we're going to do it with that. Okay. There are some situations where it would be perfectly fine to use the original one, but it's just going to provide bigger numbers. Okay. Because of that x plus 5 that is incorporated. So let's just find vertical asymptotes using that one. We have to find vertical asymptotes using that one, because if we didn't, if we used the original one, we would think we have a vertical asymptote at -5, but there's a hole there. Okay. So we use the reduced one. What's one of the vertical asymptotes? X equals -1, right? What's the other one? Okay. So vertical asymptotes are where you set the denominator equal to 0 and solve those. And if it's already factored, then that's pretty easy. Okay. Once it's factored, a lot of this stuff is just kind of recognition. Horizontal asymptotes. Okay. Again, look at the reduced version. Okay. The reduced version. What is the degree on top? 1. What's the degree on the bottom? 2. So you have x. Okay. So in general, r of x kind of looks like this. X over x squared in the long run. Okay. Because then -2 and the minus 2x plus or -3 on the bottom, they're negligible. Okay. So this in the long run, as x gets really, really big, we can really kind of cancel those out, right? That's x and that x. We can cancel one of those out. We get 1 over x. And as x gets really, really big, 1 divided by a really, 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 really big number is 0, right? Okay. And that mimics the idea that we talked about. If this exponent is smaller than the one on the bottom, the leading degree up top is smaller than the leading degree on the bottom, you will always have a horizontal asymptote of y equals 0. Okay. Now, this is one of the things that we forget to do a lot. Okay. Looking at holes is something people forget a lot, and then looking to see if we cross the horizontal asymptote is something that we neglect a lot. So let's see if we cross the horizontal asymptote. And again, we're going to use the reduced version. We're going to use x minus 2 over x plus 1 times x minus 3. Okay, we're going to see if that is ever equal to the horizontal asymptote. Well, what is the horizontal asymptote? 0. Okay? So we set that up and we want to solve that equation. Well, if I want to solve that equation, it's a rational equation. You multiply by the least common denominator, right? Multiply everything by the least common denominator. If I multiply everything by the least common denominator, what's that going to give me over here? X minus 2. And what's that going to give me over here? Okay, it'd give me, yeah, it'd be x plus 1 times x minus 3 times this 0, right? And that's just 0. So what's that give me for x? 2. That's a solution, right? Okay. It's a finite solution. Tells us that you do have a situation where you cross the horizontal asymptote. You cross the horizontal asymptote at x equals 2. Okay. The next thing we want to do is find what x-intercepts and y-intercepts. Okay. Now think about this. Your horizontal asymptote was y equals 0, right? And y equals 0 is the algebra for what axis? X-axis, right? You just determined that you cross that horizontal asymptote, which is the x-axis, only at 2, right? So what does that tell us about our x-intercepts? It's 2, okay? And if you remember what we've done in the past, okay, you could actually go through the math here. We take the numerator and set it equal to 0, right? Well, x minus 2 is equal to 0, gives me x to be 2. Okay? So if you did that math, it's fine. It doesn't take very long, right? About 10, 15 seconds, whatever. But it's the same result that you've already got. Okay? And that's the thing about understanding what y equals 0 is, what crossing the horizontal asymptote is telling me, that kind of stuff. Okay? Now the y-intercept, okay? In the last example, we didn't have a y-intercept because our y-axis was an asymptote. Is our y-axis an asymptote here? What were our vertical asymptotes? -1 and 3. So it's not an asymptote. So now we actually have to find the y-intercept. We have to take a coordinate or a quantity for x and plug it into our function. Now, if I want to find the y-intercept, what is that value of x that we use? 0. Okay, so now think about this. You've got some options. Okay, I can plug 0 into, plug in this one. Okay, if I plug 0 in there, I get what? 5, -2, so it gives me -10 up top, right? On the bottom, it'll give me 1, -3, 5, right? So it's going to be -15. Does that reduce? 2/3, right? Okay. Well, if I plug 0 in over here, what do you get up top? -2. What do you get on the bottom? -3. Does that still give me 2/3? Which one was easier? The reduced one, right? Okay. This one had that additional factor of 5 in it and made numbers bigger, right? Okay. Use the reduced version. Makes things a lot easier. So my y-intercept when x is 0, x is 0. I don't know what I'm doing. Y is 2/3. And remember, that's 2 comma 0 as well. But now we have a lot of stuff that we need for our graph, right? All right, and we could need some additional test points, but we'll see here in a little bit if they're necessary. We really only know if they're necessary once we kind of get a good start on our graph. But we had -1 as a vertical asymptote. We had 3 as a vertical asymptote. We had 0 as our horizontal asymptote. We had 2 as an x-intercept and a crossing of a horizontal asymptote, right? We had 0 2/3 as your y-intercept. Okay. And we had a hole at what? -5, 1, 2, 3, 4, 5, and -7 30 seconds.
Yeah.
which is about negative 0.2, isn't it? Okay, so just kind of estimate where that's at. So those are the points that are going to help us pretty much get everything we need in these two regions, everything we need in these two regions, but then we'll have to have a test point for these two. Okay, but here's the idea. If I've got this as a whole, okay, I'm going to treat it like it's just any other point though when we come to the graph. Okay, it's an open dot, but treat it like it's any other point. So then there should be points around it, right? Okay, and as I move to the left, I should get sucked up to that asymptote, right? And we know we should not cross that asymptote again to the left of that point because the algebra didn't show that we crossed the horizontal asymptote at anywhere but 2. Okay. Now as I move to the right, again, I know that my graph is going to have to go down because it can't go up. Because if it goes up, I would have to have had either another x-intercept or the crossing of a horizontal asymptote, right? And we don't have that. Okay. So we know that we're going to move to the right, and the graph should look something like that. My graphs always are terrible. Open dot. All right, so now we're in the middle region. Okay, so if the graph existed here, because of the nature of asymptotes, can't occur up here. Okay, so now we get in the middle. Now if I look at the middle, I know I've got my y-intercept, so I've got to go to the left, right? I've got to move to the left from that. So I've got an option of going down or an option going up. Which one does it have to be? Got to go up. Okay, because if I went down, there should have been math up there in the beginning of the problem that said you have an x-intercept of like -1/2 or -2/3 or something like that, and we don't have that. Okay. Now as I move to the right, I've got to pass through that point, right? Okay. Now, here's the thing. There will maybe be a situation where you could bounce off and go back up. Okay. But if I bounce off a point, what algebra have we learned in the past that tells you bounce off a point? Or you're tangent to a point. You'd have multiplicities, right? When we went through all that work, when we came up with 2, there was no multiplicity there, right? It was just x minus 2 as a first degree factor, okay? So that tells us what we passed through, and we're going to follow kind of that path there. Okay? And then the stuff over here, we don't know, okay? So I'm going to take my, what was it, x minus 2, x plus 1 and x minus 3. Okay, that was my function. That was my reduced function, and you can either use the reduced function or the original one here. But the reduced one is going to have a smaller factor in it, okay, or a smaller set of numbers. It removes the x plus 5 over x plus 5. I'm just going to choose a value of x that is over here and plug in there. Okay, so and I'm going to choose 4 because that's right there. Okay, so plug 4 in. Gives me the top to be 2, right? The bottom becomes 5 times 1, right? So 2/5. So at x being 4, I get y to be 2/5. That's nice because it tells me at that point 4, 2/5, okay, or 4, 0.4 is in that top region, right? So all the other points are going to be kind of similar. As I move to the right, it's going to get sucked down to that asymptote. As I move to the left, it's going to get sucked up to that one. Okay. Somebody in the last class asked, so when we break our asymptotes, or take our asymptotes and we break it up into regions like this, and we ultimately have 6 regions, right? Okay. They said we're going to have always kind of 3 graphs, 3 portions, and that is correct. We're always going to have these formats of graphs. Okay, now this thing here, this curve might be up here or down here. This one has several different things you could do. You know, it could be cubic like it is here. It might be cubic that way. It might be kind of parabolic looking, whatever. So there's some different behaviors that occur in that middle region, but these regions over here, okay, it's either going to look something like this, or it's going to look like kind of the mirrored image down here in that quadrant, that region. Does that make sense? There is times that, you know, just because you find this one down here, doesn't default this one always to be up in the top right hand corner. Okay, you could find out eventually with pictures that maybe look something like that. Okay. So once you find this, don't automatically know what that one looks like. Okay. Just has to deal with signs and powers and stuff like that. Tomorrow we'll talk about the situation where we end up with the numerator being a greater degree than the denominator. So our x value, our y values increase without bound when we choose very large values of x. So we'll talk about how to do that. Those are slant asymptotes. And then, at the beginning of class, if you guys, hopefully you look at the homework. I've extended that till Friday. Ask questions about that tomorrow. I've also extended it in regards to the amount of questions that are on it. So if you've already finished it, go back. There's about 12 more questions I've added to it. Okay? And I'm going to count that assignment as 2 homework assignments.
Oh my gosh.